we have seen the like theory portion of a solid state. Now we will move to the mathematical portion basically. So I will request everyone to join as soon as possible. And plus let me know that is my voice is clear to everyone and video is clear to everyone. Is I am audible? Is I am audible?
Yes, sir.
Okay, okay. And is my voice is clear?
Yes, sir.
Okay. Just request everyone to join as soon as possible. We are going to start. Just tell everyone that class has been started, so join as soon as possible. Okay, so let us start. So in the last class, we have seen the solid state and we have talked about the different types of solids like crystalline solid, amorphous solid, and we have also talked about another thing, that is what are the different types of crystalline solids we have. We have talked about molecular solid, ionic solid, metallic solid, okay, network solid, and we have seen that how to, like, we have done some examples also on this, okay, so that we get comfortable that how to classify them into the different things. And this is the last example which we have done. So now let us start with the next, which is very important part, that is the difference between the unit cell and the lattice, because from here only our chapter is started. So our first, just give me 1 minute. One second, just. Okay, so let us start. So our first topic is that we have to talk about that how the different types of solids are there and what are the different types of structure. So first thing we have to understand, that is what do you mean by unit cell. Okay, first thing we have to understand is the unit cell. What is a unit cell? If I give you example, suppose you see some building, okay, some building is there, or some house is there. That house is basically a, you can consider it is a structure, okay, it is a structure, but it is made up of a smallest thing. What is the smallest thing that is used for making that whole structure, whole house? The smallest thing which is used is nothing but a brick. That brick is used as a smallest unit cell that make that whole house, right? So that brick is called as a unit cell. So unit cell is nothing, it is the smallest structure, you can say the smallest part that is used to make a complete lattice. Lattice is the house, and the brick is the unit cell, simple. So what is unit cell? The smallest unit, you can say the smallest unit which repeat itself which repeat itself over the entire lattice. Over the entire lattice. For example, like a house. House is what? House is a lattice. House is a lattice. And the brick which is used here, that brick is what? Brick is the unit cell. Are you clear? Are you able to get this point? That what is basically difference between a lattice and a unit cell? Clear? Now the next thing is that what is the different types of unit cells we have? Okay, what are the different types of unit cells we have? Types of unit cell. Okay, so our first type of unit cell is primitive unit cell. Primitive means primitive. Okay, unit cell. Primitive unit cell means the cell which is conventional, which is very old. That is called as a primitive unit cell. Old unit cell is a primitive unit cell. Simple. That is a primitive unit cell. And this is called as a simple cubic. Simple cubic unit cell. Okay, simple cubic unit cell. Okay, simple cubic unit cell. Second, we have a classification. Second classification is non-primitive unit cell. Non-primitive, non-primitive unit cell. And the non-primitive unit cells are, for example, the first unit cell is BCC. BCC is called as a body. It is called as a body centered unit cell. Body centered unit cell. Second, we will have a FCC, that is called as a face centered unit cell. Remember, this chapter is very easy. It is, if you are able to do the proper imagination of your room, if you are able to imagine this room properly, whatever room you sit, you are able to do all the questions of this chapter. It is very easy chapter. Okay. Then we have ECC. That is EC, or you can say that is edge centered unit cell. So these are the different types of unit cell we have. Okay, different types of unit cell in this chapter, and some other unit cells are also there, like SCP and others are there. We will discuss that in later. They are the special type of unit cell. They are formed by the special type of geometry configurations. We will discuss that. But this is the different types of unit cell which we have to study in this chapter. In this basically subject, in this topic, we have to study all these unit cells and in detail. Okay, so let us start. Till here, everything is clear. What are the unit cell? Unit cell is nothing, the smallest unit that make that complete lattice. Okay, or you can say if there is a house, the bricks are called as a unit cells, and that house is called as a complete lattice. Okay. So second thing, what are the different types of unit cells we have? Unit cell means that is smallest repeating unit, because that suppose I have a house, that small brick is going to repeat everywhere, right, to make that complete house. So that brick is important for me, that house is not important for me. The important thing is the brick, how the brick look like. That is what the important thing. Similarly, here also we are not going to talk about the lattice is not important for me. The important thing is that unit cell which is going to repeat itself, that is very much important for me. And there are the different types of unit cell we have seen. Okay, that is primitive means simple cubic unit cell. For example, simple cubic. Primitive means conventional. Meaning of primitive is conventional, that is a normal which exists in the which is a conventional unit cell. Okay, and non-primitive means which is basically not conventional, some other type of variations will be there. Okay, we will discuss that variations. So till here everything is clear. Till here everything is clear.
Yes, sir.
Okay, now the next thing is, see, what are the parameters of a unit cell? See, I have to design a different unit cell. I have to make a different unit cell. So we have to define some different parameters. Okay. So what are the parameters of a unit cell? Parameters of unit cell. Okay. So there are two types of parameters are there. Okay. One is called as a inter x. One first we write it as a b c, and second is alpha beta gamma. What is ABC? What is alpha, beta, gamma? See, ABC is called as an interaxial distance. It is called as a interaxial distance. This is inter. I will explain it. No problem. No, just no problem. I will explain. interaxial distance. This is called as an interaxial distance. And alpha, beta, gamma is called as a, they are called as a interaxial angles. They are called as a interaxial angles, right? These are the two important parameters are there. How they are important, let us see. Let us try to understand how they are important. Suppose this is my x-axis, this is my y-axis, and this is my z-axis. Suppose this distance is considered as a in x-axis, this distance is considered as b in z-axis, and this distance is considered as c in x-axis. The angle opposite to a I call it as alpha, angle opposite to b is called as beta, angle opposite to c is called as a gamma. Okay, so if let us, I give you one example. So how these are important? So if I ask you in cube, are you able to connect in cube? In cube, what is the property of a cube? A cube have all the sides are equal to each other, right? The cube in cube, all the sides are equal to each other. So if I want to make a cube by using these parameters, I have to make a equal to b equal to c. First condition. Second condition, that all the angles will be 90-degree, right? In a cube, this all angles will be 90-degree. If you imagine your room, just try to imagine your room. In room, this is my a, this is my b, this is my c, right? So a, b, c, all sides are perpendicular to each other, right? They are making 90-degree angle. So I can say my alpha is equal to beta is equal to gamma is equal to 90. So this is an example, 90-degree, right? So this is an example of one of the example, like how we design a different geometry by this parameter. So I hope you are able to connect it. If by choosing the different value, like you can get the different parameters. Okay, if I choose properly, I can make the different type of geometry depending upon these six parameters. These six parameters are able to generate a different types of geometry. Okay, so just note it down. These six parameters are very important, and by these six parameters, we have almost 14 different types of lattice structures are there that are met by using this. Like by using these six parameters, we will have to study all those. Okay, completed. So, what are those different types of lattice are there? So let us see this. Okay. Okay. So if you talk about the geometry, what type of geometry we get? Okay, so crystal lattice, what type of different types of crystal lattice we have? Then we have a axial distance. Okay, then we have a axial angle, and last we have a unit cells, also called as a Bravais lattice. Okay, so what are the different types of crystal lattice we have? So I'm writing the name. First is cubic, Second is rhombohedral, rhombohedral. Okay. Third is tetragonal. Then hexagonal. Then we have a orthorhombic. Then we have monoclinic. Then we have a triclinic. So these are the different types of structures we have got. Now, what are the different cases of axial distance? So different cases for these are: first A is equal to B is equal to C, then A is equal to B is equal to C, then A is equal to B is equal to not equal to C, then A is equal to B not equal to C, then A not equal to A not equal to B, B not equal to C, then A not equal to B, B not equal to C, then A not equal to B, B not equal to C. So it is very easy to remember. If you see, there is a pattern is there. Okay, this pattern is there. First A is equal to B is equal to C, then A is equal to B but not equal to C, and then so if you are able to get this pattern, you are able to remember it. This is the first pattern. Okay, just try to remember in this pattern only. Okay, second is axial angles. So first is this. For this also we have pattern: alpha is equal to beta is equal to gamma equal to 90. All are 90, that we have seen also. Alpha is equal to beta is equal to gamma, but that is not equal to 90. Clear? Second, again alpha is equal to beta is equal to gamma is equal to 90, but again here also alpha is equal to beta is equal to gamma is equal to 90, but gamma is equal to 120. Alpha is equal to beta is equal to 90, but gamma is equal to 120. Okay. Next case, again alpha is equal to beta is equal to gamma is equal to 90. Then alpha is equal to gamma is equal to 90, but beta is not equal to 90. And last case, alpha is not equal to beta is not equal to gamma is not equal to 90. So this is how you can remember for this. So here you can see also there is a one pattern is going on. Just try to see. First is alpha is equal to beta is equal to gamma is equal to 90. Then alpha is equal to beta but equal to gamma but not equal to 90. Okay. Then again same thing. Again alpha is equal to beta is equal to 90 and gamma not equal to gamma equal to 120. Then again same thing. Alpha is equal to beta is equal to gamma is equal to 90. Then alpha is equal to gamma is equal to 90 and beta not equal to 90. Okay. Another and last one is very easy to remember because in triclinic it is a most unsymmetric structure. You can see all the sides are unequal, all the angles are unequal, and they are not equal to 90 also. So this is the most unsymmetric. And what are the different types of unit cells we have? Here we have a 3. Sorry. Here we have a 3. Here we have a 1. Here we have a 2. Then 1. Then 4, 2, 1. 3, 1, 2, 1, 4, 2, 1. 3, 1, 2, 1, 4, 2, 1. Right? Like that you remember it. 3, 1, 2, 1, 4, 2, 1. If you try to remember like this, then it will be easier for you. Okay. 3121 421. 3 means it will have a what type of structure? Simple cubic, body centered, and FCC. All three structures are there. One, it will have only simple cubic. Two, it means it will have simple cubic, then BCC. Okay. It is better you can write like this also. Simple cubic, body centered, BCC. Then we have face centered cubic. One means simple cubic. Four means simple cubic, body centered, BCC, FCC, and S centered, ECC. Then we have a SC, simple cubic, and edge centered. And last is simple cubic. Okay. So this is how it look like. See, we are going in order. Simple cubic, then BCC, then FCC, simple cubic, two simple cubic BCC, one simple cubic, four. All the types of unit cells will be there. Only this is the special case. Only this is the special case. If you are able to get this, this is one of the special case that here we have only EC. In any other case, you won't find EC. This is the EC. Okay. This is also simple cubic. So this is the different type of structures which are obtained after taking those parameters value in different combinations. Okay. And how to remember it? See, this one you have to remember. There is a no trick for this. Okay, this you have to remember. But if you remember this in this order, then writing these other things are very easy too. Okay, for this how to write A equal to B equal to C, then A equal to B equal to C. This is the two block. Then A equal to B not equal to C, A equal to B not equal to C. Second block, then A is not equal to B is not equal to C three times. Like this you can remember. Now how to remember the angle? First thing is clear. Alpha is equal to beta is equal to gamma equal to 90. Alpha is equal to beta is equal to gamma but not equal to 90. Then second, alpha is equal to beta is equal to gamma is equal to 90. Then alpha is equal to beta is equal to 90 and gamma is equal to 120. Then next, alpha is equal to beta is equal to gamma equal to 90. Then alpha is equal to gamma is equal to 90 and beta is not equal to 90. And the last case is alpha is not equal to beta, not equal to gamma, not equal to 90. That is how you have to remember. Now 3121 421 3121 421. Like that you can remember all the things. Okay. This is how you have to remember everything. But just you have to remember these names. After remember this name, it is very easy to write this in this order, right? Is it clear? Is it clear to everyone?
Yes, sir.
Okay. Just note this down. Note down this table. Okay. You can take the screenshot also. Take the screenshot. Okay. Now let's note down some important points regarding this table. Some important points. If I ask you which is the most symmetrical, okay, first point is, or let us say first point is total number of crystal lattices. How many crystal lattice are there? Total number of how many crystal lattice are there? 7. We have a 7 crystal lattice. So total crystal lattice is 7. Okay. That is the first important point. Second important point is what is the second important point? Total Bravais lattice. Total Bravais lattice. How many total Bravais lattice is there? There are total 14 Bravais lattice are there. How 14? You can count also. See, 3, 1, 4, 4, 5, 6, 7. 7 plus 6 is, sorry, 1 minute. 3, 6, 6, 7, 8, 5, 6, 7, 7, and 4, 5, 6, 1, 7. So total is 14 years. So this is the 14 Bravais lattice are there. Okay. Most symmetrical lattice. most symmetrical lattice. Which is the most symmetrical lattice? If you see this table, most symmetrical is cubic. See, A equal to B equal to C and alpha is equal to beta is equal to gamma equal to 90. Everything is same. Okay. In any other case, you won't get. So this is the cubic. Okay. Cubic. Third point, most unsymmetrical lattice. Most unsymmetrical lattices, which is most unsymmetrical. If you see the last one is most unsymmetrical, that is triclinic. In triclinic, all the sides are unequal, all the angles are unequal. So it is triclinic. Okay. Next is what is the geometry of a matchbox? Geometry of matchbox. See, if you try to understand in matchbox, everyone have seen the matchbox, right? In matchbox, one thing is very fixed, that all the angles are 90. If you see the matchbox, all the angles are 90. That is always true. So which can be the possible? Either this will be possible, this will be possible, or this will be possible. So either three geometries can possible: cubic, tetragonal, or orthorhombic. That is a three possibility will be there. Okay, no other possibility can be exist. Only three possibilities are there. Now if you see the matchbox, this is the height of the matchbox, this is this length, and this is this length. You can surely say that, sir, this is the smaller height, then this side is very large, then this side is little small. Okay, all the sides are unequal in a matchbox. All the sides are unequal in a matchbox, and all the angles are 90 degrees. So it has a orthorhombic structure. So for a matchbox, it is a orthorhombic in nature. Orthorhombic. It has a orthorhombic structure. Clear? So this is a different types of important points are there within the table. If you have to must remember these points. Okay, just note it down. Note down these points. One more thing, if you have any doubt and you want to contact me, again contact me on this number 8381 950 386. Okay, this is my contact number. You can message me over this, don't call. Okay, just only message. You want, you can note it down. If you have any doubt, you can send me on this. Okay. Clear? So let us proceed further. Now we will go to and start our discussion to the different types of unit cells. So first unit cell we are going to discuss is simple cubic unit cell. That is our first unit cell we are going to discuss. So let us start with the first unit cell, and it will be very easy for you. Okay, I'm giving you one thing guarantee, it will be very easy to like understand the things. Just you have to follow. So suppose this is my cube. Okay, first I would like to tell you some important points regarding cube. Okay, First some important points regarding Q. Just for now, you just remove this. You should know some important points about the Q. Important points regarding Q. Okay, first tell me. I will ask you one thing. Just answer me. How many corners are there? How many corners in a cube? How many corners are there in a cube? How many corners are there in a cube?
8.
There are 8 corners are there in a cube, right? Second is, how many faces are there? How many faces in a cube? How many faces are there? How many faces?
6.
Yes, there are 6 faces are there. Third, how many edges in a cube? How many edges in a cube? How many edges? Edges, you understand? This is called one edge. Another edge. 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 12 edges are there. Okay. You can say 12 edges. This is the edge. This thing is the edge, right? This thing is the edge. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 edges are there. Clear? Next. Do you understand what is this line? If I draw one line, I ask you what is the meaning of this line? Okay, 1 minute. Yes. Suppose I taking this corner and I'm joining this corner. What is this line called? This line. This is O. This is A. OA. What is the meaning of OA? OA is touching the two opposite corners, right? It is touching the two opposite corners. It is go one that room corner, another this room corner. So it is a line which is the opposite corner, which is touching the opposite corners of the room, right? So this is called as a body diagonal. This is called as a body diagonal. Body diagonal. And what is the length? The length is root 3a. If a is the side of the cube, obviously a is the side of the cube. We are talking about cube, okay? Just write it here, otherwise you will be confused. So we are talking about every discussion is going on for cube, okay? Second thing, my second important point. Suppose I draw a one line going like this. This is letters B. Okay. So what is this AB line? What is this AB? AB, if you see, it is touching the opposite corners again, but on the one face, right? This is the one face. It is touching the corners, but on the same face. It is called as a face diagonal. This is called as a face diagonal. And what is the length? Length of the face diagonal is root 2a. So if I ask you how many face diagonals are there? How many? How many face diagonals? Can anyone tell me how many face diagonals will be there? How many face diagonals will be there?
6.
On one face, how many face diagonals we can draw? Suppose I take one face, okay? How many diagonals you can draw on one face?
2.
And there are how many faces?
12.
There are how many
6
faces?
face.
6. 6 into 2?
12.
12. So how many diagonals will be there? Face diagonals?
12.
Yes. So how many face diagonals are there? 12. Similarly, if I ask you how many body diagonals? How many body diagonals? How many body diagonals are there? Just try to imagine how many body diagonals we can draw. See, one I can draw from here to here, okay, opposite corner. Second one I can draw from this corner to this corner, right? So one I can draw from here to here. Second I can draw from here to here, right? Similarly, one I can draw from this point to this point, and another one I can draw from this to this point. So in a cube, how many body diagonals I can draw? Body diagonals means nothing, just you have to go from one corner to the another opposite corner. So if here I am going from here to here, similarly I can go from here to here, right? Then I can go from here to here, then I can go from here to here. So there are the four body diagonals can be drawn. Okay. So how many four body diagonals are there? Four body diagonals are there. How many body diagonals? Four body diagonals are there. So this is the different important points regarding the cube. There are a lot of other points are also there, but these points are more than sufficient, okay, for you. Clear? So you should remember all these points because this cube is going to come again and again in all the types of lattice. So it should be very much familiar with you, okay? Sorry. Clear? Sorry. Clear? Okay. So
Yes, sir.
further, now we can start studying the different types of unit cell. So first is simple, cubic unit cell. So let us talk about first simple cubic unit cell. So let me draw a geometry for you. Maybe in diagram it don't look proper, but whatever I write and whatever I tell, just focus on that, okay? Because it's a 3D geometry and 3D cannot be drawn no, properly. Basically, it will have atoms at its corner, okay? Wait. This is one atom. This is another atom. This is another atom. This is one atom. This is one. This is one. This is one. This is one. All atoms are symmetrical only. Maybe I'm not able to draw it properly, but all atoms are symmetrical. So first important point. Atoms are present only at the corners. Atoms are present only at the corners. First point. Second point. This atom is going to touch this atom, this atom, this atom. Okay, just try understand very properly. Okay, very slowly I am going. It's slightly difficult part. This atom will going to touch this atom, will touch this atom, and will touch this atom also. So are you getting my point? It's like this one atom is touching these three different atoms. Okay, this one atom, actually how it is look like, let me draw it in more like more bigger way. If you try to see, it will be something like this. Suppose this is a one atom, and there will be one another atom will be there. Okay, this is another atom, and they will be like this. I think size is not as small. Yes. Okay, this is like this. One atom is touching this atom also. This atom is touching this below atom also. Okay, and this is also touching this atom also, like behind the screen. You can say it's a behind the screen. It is like something like this. Okay, so like this one atom is touching these three atoms. Okay, like this. So one more thing, this corner, sorry, this corner, all these corners is all the corners are present on the centers of the atom, right? All the corners are present at the centers of the atom. Okay, the corners are present at the center of the atom. Clear? That is the second point. Third important point, at corners, how much sharing is there? At corner, we have 1 by 8 sharing. Means one atom share the 1 by 8th portion. If you see at the corner, one atom is sharing 1 by 8 portion. How many atoms are there? So there is something we define called as a Z effective. What is Z effective is there? Z effective is basically defined as a, suppose I take a one unit cell, how many effective atoms are present in a one unit cell? Z effective is how many effective atom in one unit cell. So here you can see, if we want to calculate Z effective for a simple cubic unit cell, there are 8 atoms are there, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms are there. Every atom has a sharing of 1 by 8 because they have present at the corner. At the corner, the sharing is 1 by 8. So how many effective atoms are there? Only one effective atom is there. So overall, if you combine this, you will get only one effective atom. That is the meaning of this. Second thing, as we can see, these two are touching each other, like, right? Suppose this is my center, right? And this is the center of this, and this is the radius of this atom, this is the radius of this atom. So next important thing is third, this is fourth point. Now fifth point is something called as a relation between atomic radius and edge length. Edge length means A and atomic radius R. Okay, this is my edge length. Clear? This is my edge length. Sorry, this means I edge length, that is A. So you can see properly here, my 2R is equal to how much? A. So my R is equal to A by 2, right? Simple. So remember this, R is equal to A by 2 is the relation between the edge length and the atomic radius in simple cubic unit cell. Clear? Second last important point is the which is very important, that is CN, which is called as a coordination number. coordination number. Coordination number means nothing. How many atoms are touching this single atom? Okay, coordination number means how many atoms are touching a single atom is called as a coordination number. If someone asks you what is a coordination number, that means it is asking how many atoms are touching each other. Okay, suppose I pick a one single atom and I ask you how many atoms are touching this single atom. That is called as a coordination number. Okay, coordination number means number of atoms touching a single atom. So for simple cubic unit cell, for SCC, what is the coordination number? If you see, this atom is touched by this atom also, this atom also, this atom also, and similarly, this going to be repeat here, right? This going to be repeat here also, above also, below also, right? Are you getting my point? This is not a single. I have shown you single, but it will be there will be repetition will be there, right? Because it's a unit cell, so it is going to repeat itself. So there will be similarly there will be one above will be also there, one here also, one here also. So if you see, this atom will be touched by this, and similarly there is a one other atom at this point, one other atom above also, and similarly one other atom right this also. Clear? So it is going to be touched by other because this geometry is going to repeat itself. Okay, so this atom is touching three other atom outside also. So total coordination number will be for simple cubic unit cell is 6, because that means one atom is touching the 6 different atoms. One atom is touching the 6 different atoms. So this is about the simple cubic unit cell. What is, again, just repeat it. In simple cubic unit cell, the atoms are present at the corners. Each atoms are touching, each corner atoms are touching other corner atoms. Okay, like this atom is going to touch this atom, this atom, this atom, but it will not touch this. Okay, second thing, in a corner the sharing of a atom is 1/8. So what is Z effective? Z effective means how many effective number of atom present in a unit cell. So Z effective, if you want to calculate, there are 8 atoms are there and they are present at the corner. What is the sharing at the corner? That is 1/8. So Z effective will be 1. Second, relation between the atomic radius and the edge length. See, as the two atoms are touching at the edges, right? So this distance should be, these are touching each other, right? These are touching each other. So this distance should be equal to A. So from here we got R is equal to A by 2. Second relation. Third important point is coordination number. But how many atoms are touching a single atom? So if you see, there will be total, it look like there is only 3 atoms, but it will be repeat itself, right? This geometry is going to repeat itself. So there will be total 6 atoms will be there that is touching each other. Okay, so this is about the simple cubic unit cell. Similarly, we have to see for body centered unit cell. It is clear? Is it clear to everyone?
Yes, sir.
Okay, now next is body centered unit cell. Okay, that is called as a BCC. If I show you the geometry, how the BCC look like. This is a geometry of BCC. In BCC, we have, just a second. Yes. See, all the atoms as present in the simple cubic unit cell, similarly here will be also there. Okay, all the atoms will be at the corner. There is no problem with this. But what is different in BCC is that, let me show you once. Okay, what is the difference in BCC? There will be one atom which will be completely inside this, at the center, inside this cube. Okay, this is the one atom which is completely inside this, and the most important thing is that this atom will touch all the other atoms. It will touch this atom also, it will touch this atom also, it will touch this atom also, it will touch this atom, it will touch this 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 all the atoms. Okay, all the atoms are touched by this atom. So the important points, first is atoms are present at corners and center of the cube. Center of the cube. In this case, like center atom touch all the corner atoms. Remember, I am saying only center atom touch all the corners atom. Now corner atoms will not touch each other. Okay, that is only valid in the SCC. In simple cubic unit cells, only the corner atoms are touching each other. Now in this case, the corner atoms won't touch each other. Okay, they won't touch each other. Remember this thing. Okay, don't confuse with that they will touch each other. No, they won't touch each other. Okay, now only the corner atoms won't touch each other. It is only it is only touched by the center atom. Okay, center atom is going to touch all the other atoms. Remember this thing, it is not going to be touched by the corner atoms. Means what is the important thing, that corner atoms will not touch each other. Okay, only the center atoms. Okay, only the center atom is touching all the other atoms. Simple, that is the simple thing. Means this is a center atom, this will touch this atom also, this atom also, this atom, this atom, this atom, this atom, this atom, this atom. All atoms will touch each other. You can go in the internet and you can search the 3D structure of BCC. That is, you can search like this and you can see also. Okay, you can search 3D structure of BCC. After the class, just go once and search it. I don't have a model right now, otherwise I will show you. Just go and search BCC structure and you will see and you will understand that what I am trying to say. Okay, so this is about the second point. Third is what is the third important point? Okay, see, at corners we have how much sharing? We have 1/8 sharing, right? We have a sharing of 1/8. At center, how much sharing will be there? We have complete one sharing. Okay, complete one sharing is there in center. So if I ask you what is Z effective? Z effective, see, 8 atoms at the corner multiply by the sharing 1/8. One atom at the center multiply by the sharing 1. So Z effective will be 2. Means there are effective 2 atoms are there in a body centered cubic cell. Effective 2 atoms are there in a body centered cubic cell. Clear? Clear? So basically, what is this 8 atoms at at 8 corners. Remember this, okay? It's very important structure, so you have to remember this. 8 corner and one this atom at body centered, okay? Body centered, okay? So this is the thing. Now second is z, if sorry, relation between a and r. So if you see properly, you will understand my geometry is something like this, right? This one atom is touching the another opposite atom, right? So it is something like this. Suppose this is my one atom, okay, and there is another atom is also there. So it is something like this, okay? So suppose this is my center, this is my center, and this distance is r, this distance is r, and this is the, like, I'm taking these two atoms, okay? I'm taking these two atoms, right? So this is my body diagonal, right? So I can say my 2r is equal to body diagonal, half of the body diagonal, because I am talking about these two atoms, right? So half of the body diagonal. What is the length of body diagonal? Root 3a. Okay, and half of the body diagonal will be root 3a by 2. So that is a relation between r and edge length. That is a relation between r and edge length. Clear? That is a relation between r and edge length. Now next, last important point is coordination number, like how many atoms are touching each other. So if you see, there is an atom at the center. How many atoms are touching that atoms which is present at the center? How many atoms are touching the atom which is present at the center? This atom is going to be touched by all the 8 atoms, right? All the 8 atoms which are present at the corner. So the coordination number here is 8. Okay, coordination number here is 8, because this atom is going to be touched by all the atoms, right? Okay, so the coordination number for this, or you can say coordination number, will be 8 here, right? Okay, so this is about body centered unit cell. Now similarly, we have another type of unit cell is, that is called as a face centered unit cell. Third type of unit cell is face centered unit cell. Now in face centered unit cell, what we have did, just let's see the geometry for face centered unit cell. 3D, okay, this one, yes. Okay, so there will be same atoms will be present at the corner as earlier it is there. Okay, I'm drawing a small because I have to draw a lot of atoms. So there will be atoms at the corner as it is present earlier also, but there will be slight difference will be there. Let me tell you what is the difference once I complete it. Corner atoms will be there as it was present earlier also. Atoms at the corners are there. Okay, there is a no change is there. They will be there. But what is the difference? Okay, let us talk about the difference. There will be some other atoms will be also there. What are those other atoms? There will be one atom at the center. One atom not at the center, at all the faces we have a one atom. At all the faces we will have a one atom. One atom at all the faces. This is back side. Okay. Like this. Okay. So you can see at all the faces we have a one atoms will be there. So initially what happened? Initially in simple cubic unit cell we have atoms only at the corner. In body centered unit cell one atom will be present at the center. In then we have seen now it is FCC, face center unit cell. In face center unit cell, one atoms will be present at every face. We have a one atoms. As initially in body centered unit cell, only the body center atom is touching the other atoms. Here also, only the face centered atoms is going to touch the other atoms. Okay, means this atom is going to touch this atom also, this atom also, this atom also, this atom also. What I am trying to say, this face centered unit cell, face centered atom is going to touch this. Okay, they are now this as atoms cannot touch each other. This is not possible. They can't touch each other. Okay, as similarly as we have seen in the previous case also, the body centered atom is going to touch the other atoms. Corner atoms are not touching each other. So let me write the thing. One important point. First important point: the atoms will be present at the. We have a 8 atoms at 8 corners, right? We have 8 atoms at 8 corners, plus we have one atom at every, we have 6 atom at 6 faces. You can say 6 atoms at 6 faces. This is another important point. Second, what is the sharing at face? See, sharing at corner is 1/8. Sharing at face is 1/2. So what is my Z effective? Sorry. What is my Z effective? Z effective is 8 corner atoms, sharing is 1/8. 6 face atoms, sharing is 1/2. So what is Z effective? That is 1 plus 3. So effective atoms is 4. There are 4 effective atoms are there. Now second thing is coordination number. See, if you see, this atom is touching this atom, this atom, this atom, this atom. So suppose this is my room. Okay, try to imagine it. Suppose there is a one atom at the ceiling, at my top. Okay, this atom is touching that corner atom, that corner atom, that corner atom, that corner atom. So 4 atoms are touching this. Now similarly above this room there is another room is there, right? So that ceiling is now becoming a floor for the another room, right? And this atom which is present at the face, half portion in this room and half portion is the above room, right? So the half portion which is the above room will also touching the 4 corner atoms. Are you getting my point? Suppose you try to imagine it. Okay, suppose this is my face. Okay, there is one atom at the face center. Now this face center atom have half of the portion in this room and half of the portion in the adjacent room. So half of the portion which is in this room is touching the 4 corners atom, right? And similarly the half of the portion which is in the adjacent room is also touching the 4 corners atom. Are you getting my point? Are you able to understand what I'm trying to say?
Yes, sir.
Okay, so what I'm trying to say, this atom is touching the 4 corner atoms of this room, 4 corner atoms of that room also, and also this atom is going to touch the this atom is going to touch this atom also which is present on this face, and this atom also which is present on this face. Let me try to explain properly. Try to imagine, suppose there is a atom at the at our this is my face, there is a one atom at the face center. First thing is very clear, this is touching the 4 corners, this is clear. Now what is going to be happen, just try to imagine, this atom is going to touch the atom which is present on this face, the atom which is present on this face, the atom which is present on that face and the atom is present on that face. Are you getting my point? Means what I am trying to say, this single atom is touching the corner atoms also and the atoms which are present at the faces also. What I'm trying to say, this atom is touching the corner atoms also, and it is also touching the atoms which are present at the faces also. Means suppose there is a one atom at this face, it is touching the four corners. 1, 2, 3, 4. Four corners are covered. Now this atom will touch the atom which is present at this face center. This atom will touch the atoms which is present at this face center. This atom will touch the atom which is present on this face center. This atom will touch the atom which is present on this face center. So total four atoms it can touch which is present on the face center on this room. Similarly, there is a four atoms it can touch on the another room which is present on the faces. So there are four atoms on this room, four atoms on that room, and four corners. So total 12 atoms it is touching. One atom is touching the 12 atoms. Are you getting now? Now it is clear to you how the atom is touching each other. Is it clear?
Yes, sir.
So try to understand again. There are four atoms at the corner. Okay, it is touching the four corners atom. I'm writing like this because it is little complicated. Second, four atoms of phase in same room. Okay, plus four atoms of phase in adjacent room. In adjacent room. So total number of total coordination number will be 12. Clear? And similarly, if I ask you the relation for A and R, so you can see that this is my one atom and this is my another atom, right? This is my one atom and this is my another atom, and it is touching the corner, right? So if it is touching the corner, suppose this is my center, this distance is r, this distance is r, this 2r, and if it is touching a like phase diagonal, it is a phase diagonal. What is the length of a phase diagonal? Root 2a. Half of the root 2a is root 2a by 2. So this is a relation for the r and edge length. Clear? Is this geometry is clear? This is a very important geometry because this has a maximum packing efficiency. You can see the atoms are very closely packed because the coordination number is very large. Okay, in this the atoms are coordination number is 8, very small packing is there, but this is very weak. Why? Because the coordination number is very small. If you can see, coordination number is only 6. Okay, now last type of geometry I would like to tell. 1 minute. Oh, sorry. Should not add a slide here. 1 minute. Yeah. So last type of geometry, which is not that much important. We will not go that much detail in there. Like last is, no one asked this also, S-centered cubic unit cell. If you talk about S-centered cubic unit cell, this is no need to discuss like lot of things about it. You just know what is the geometry look like. Okay, no one ask anything. Say this is my cube. There will be, it's a very simple geometry. There will be atoms at the corner. Okay, and there will be atom any two opposite faces, any two opposite face. Okay, simple, any two opposite faces you can take. I am taking this, you can take anyone. So first thing, 8 atoms at 8 corners. plus two atoms at opposite faces. Opposite faces. Okay, that is a first property, like first important point. So second is sharing. Now sharing, so you can calculate Z effective also. Z effective, 8 atoms at the corner, packing like sharing is 1 by 8. 2 atoms at the faces, sharing is 1 by 2. So what is Z effective will be? It will be 1 plus 1, that is effective atom is 2. Okay. Now no need to find coordination number and other this thing. You can just leave it here. That is more than sufficient for this. Okay. Clear? Any doubt till here? Till here, any doubt is there?
No doubt, sir.
Okay, so
No, sir.
let me make a simple summary for you, like what you have to remember. Okay, I'm writing a simple summary. You should know this thing one day. Okay, summary 1, 2, 3. First is simple cubic SCC, then BCC, then FCC. Okay, what are the things you have to remember in all these geometries? We have a lot of things we have studied, but what you have to remember, you have to remember simple things. First thing is coordination number. Second is uh, a and r relation. Okay, and what are the other things can be? Z effective. Z effective. So if you see these things, some simple cubic unit cell, what is the coordination number 6? What is a and r relation? That is 2 times of, sorry, 2 times of r is equal to a. What is Z effective? Z effective is 1. Similarly, BCC. If you talk about BCC, in BCC we have 8 coordination number. What is the relation? 2 times of r is equal to root 3 a by 2. What is the Z effective? Z effective is how much for BCC? That is 2. Similarly, what is the coordination number 12? This is 2r is equal to root 2 a by 2. And what is the coordination number? Sorry, what is Z effective? Z effective, if you will see, it is 4, right? So remember that coordination number increases. So packing packing efficiency efficiency increases. As you increase the coordination number, there will be more packing efficiency will be there. More coordination number, more packing efficiency. So we can say FCC has a higher packing efficiency than BCC and then SCC. So generally, whatever the ionic compound you have seen, all the ionic compound will have a FCC structure. NaCl has a FCC structure. Okay, if you see the NaCl, there will be atoms which are present at the corners, and there will be the atoms which are present at the faces also. So generally all the molecules try to follow the FCC structure because it is very, you can say, very high packing efficiency is there. If you calculate, you will get 76% of packing efficiency. There is another type of one more geometry we will develop when we do the like adjustment of the atom, that is called as a SCP, hexagonal. It is a hexagonal pyramidal structure, type of structure is there, and like SCP is also another which has a maximum efficiency, packing efficiency of 76% only. Okay, we will see that also. Before going to that, tomorrow we will do some numericals. Before that, let us do some one simple example, so that you will be confident about what we have learned. So one example we will do. Okay, an atom is crystalline in BCC unit cell of edge length 300 nanometer. What is the radius? What is the radius of the atom? Radius of the atom. Solve and tell me the answer. What is the radius of the atom? Or let us make it slight easier. The calculation will be tougher otherwise. 300 root 3 nanometer. Okay. What is the radius of the atom? Solve and tell me the answer. Solve and tell me the answer. What is the radius of the atom? See, it is a BCC type of unit cell, right? It is BCC, right? In BCC, you just tell me what is the relation between A and R. In BCC, what is the relation between A and R? What is the relation we have seen? In BCC unit cell, what is the relation between A and R?
R is the radius, A is the edge length.
That I know. What is the relation? What is the relation you have studied? In BCC unit cell, what is the relation you have studied? 2R is equal to root 3A by 2. That is the relation between the radius and the edge length, right? So just use this formula now. Here, just use this 2R is equal to root 3A by 2, right? Now, edge length is given, right? Just put it here. Root 3 into 300 root 3 nanometer divided by 2 is equal to 2R. So we have to calculate R. That will be root 3 into 3, that is 3 into 300 nanometer. This 2 will come down, so it will become 4. So this is 900 by 4 nanometer. That is a radius. Simple. I'm saying that this chapter is very easy. The questions, everything will be very easy. It will be from there only. What is the value? 8, 1, 2, 5. This is the radius. 255, 225 nanometer. Simple. These types of questions only come into the examination. I'm saying you, if you follow these notes, if you completely go through these notes now and remember each and everything, not a single problem can ask beyond these notes. That I am giving you guarantee. In chemistry, it is my guarantee. They will not frame any question out of the notes which I am giving you. Okay, it will not give any question out of the notes which I am giving you. It will be all from the notes. In physics, see, in physics the problem is there is a concept, there is not a question, there is a concept. Concept will be from my notes only. Question, they can frame anything. Its question is, it can be framed anything, but if you follow the concepts, then it is easy to solve all the types of questions. But in chemistry, I am giving you everything from my notes. Even the questions will be also from my notes. They cannot ask question beyond my notes. Okay, all the questions, everything will be from whatever the type things we are going through it, everything will be from notes. You can, in previously in 2025 also, like physics is the same. in 2024 they have asked the physics and everything is from my notes only. So if you like follow the notes properly, I am giving you a guarantee you solve everything. Okay, not a single problem will be left, everything will be solved properly. Okay. Okay, so tomorrow we will meet in the morning with the physics. I have given you some homework also to solve some question of SCB. So just solve this. Tomorrow we will meet and we will proceed further in the electric calculation of electric field and all that. Okay. Sorry. And in the next class in chemistry, we will see the calculation of packing efficiency, how to calculate packing efficiency in all that cases. Okay. Till then, okay. Bye.
Thank you, sir.
Okay. Okay.
Thank you, sir.
Okay.